Hi everybody, welcome to Calibration 2. So this is the second lecture on calibration. So far we've talked a little bit about error. What is error? How do we think of error? It's pretty intuitively a deviation from an ideal measurement. And we've developed the idea of trying to develop a calibration, that is, from data that quantifies how a sensor performs. How do we extract an equation that predicts the relationship between the measured quantity and the sensed quantity? So far what we've done, we've developed the idea of the expected value operation. So the expected value of some quantity, we said, was just the sum of all the measurements for that quantity divided by the number of measurements. And what we've said, but not really emphasized very heavily, is this is true when n is very large. So basically in the limit as n approaches infinity, that's when this becomes true. This is not so much, for example, I can disprove that, or I can prove that why that has to be true. If you just consider the case, what if n's 1? Well, then that's clearly not going to be true, right? So we haven't really emphasized that very heavily yet, but that's the case. Anyway, so when n is large. So we developed the idea of the expected value, and we set up this, we also set up the idea of variance. So we developed that idea. So the variance of x, we said, was the same thing as the expected value of error squared of x, which was the expected value of the difference between x and its expected value squared. Whoops, that should be a parenthesis. That should be a bracket. There we are. Which is just this. And again, in the limit when n is very large, this is irrelevant, right? So in the limit when n is very large, this is irrelevant. So we developed these ideas, and we also developed this concept here, which was the problem that we're trying to solve, which is so here in this example, the measurement might be pressure, let's say, and then the observed might be voltage. So if we, for a sensor, let's say a pressure sensor, we might be trying to measure pressure, and we might be looking at the voltage coming off of that sensor. And you develop, of course, a series of you come out here. If we're using a NIST calibration approach, then you do this. You skip measurements, and then you come back and fill in. All right, so this is what we did last time. We got this far. All right, so last time we also showed that if we want to use a calibration of this form, y is equal to mx plus b. If we want to use a straight line to try to approximate these data, then, well, we came up with expressions for this. We showed that the expected value of x times y for all of these data points is equal to m times the expected value of x squared plus b times the expected value of x. And we showed that this is also true. So we developed a system of two equations and two unknowns, and when we solve them for m and b, make sure it's in shot. Yeah, we're good. There we go. That gives us the slope, and then we can just get the offset b by solving for it. No problem. All right, so that's where we left off last time. So let's do a couple of quick examples. So now I'm not going to use, normally you'd have big data sets, the bigger the better, right? So 10 points is kind of a typical minimum in calibration. The absolute minimum is 2 points for linear calibration. That's a very poor linear calibration. 10 is more, 5 to 10 is more typical, 20 is quite good. So that's sort of the typical number of points used to calibrate a sensor. Okay, so we'll use a small number, let's say 5 points, just to make the data set manageable. So I need to make a table. So if I have a series of x points, again, these might be, you can go either way. You can do this with with volts on the horizontal axis, or you can do this with PSI on the horizontal. It doesn't actually matter. You'll get a straight line either way. You just need to remember which one's which, right? And that'll tell you which one you're doing this for. So the same analysis can work either way. Interesting thing, you do get slightly different answers if you flip the axes. Very slightly different. I wonder why. I'll let that question hang out there. I won't answer it today. Okay, let's do a thought experiment and pretend that we go into the lab and we take a series of measurements with very well-known pressures, and we measure a series of voltages. All right, so what pressures shall we measure? Let's measure 0.1 psi. Let's measure precisely 10 psi. All right, let's measure 20 psi. All right, now let's come back and measure. So we need what? 2 more, yeah. So let's say 15 psi and 5 psi. So these are all in psi. So let's assume this is a 0 to 20 psi sensor. So this would be a pretty decent way of doing it. Notice I didn't actually write exactly 0. In reality, we probably wouldn't have exactly round numbers here either. It depends on how good we are at specifying these. All right, now here, these are certainly not going to be round numbers because these are going to be nice, messy measurements, right? So this might be, I don't know, 0.4 volts. And let's see, what might this be? This, give me just a minute, I will be with you. I just need to think this through. Yeah, so let's just call it something like that. And yeah, that could be doable. Okay. And this would end up being about, we'll call it 3.3, why not? Maybe 1.0. So I have deliberately injected, it took just a moment's thought, so this is data that could be real in volts, but I've deliberately injected error. Actually, I've injected more error than I would expect to really see in this system. This, if we plotted it, would probably not be a very good calibration. All right, so now we need to, in order to calculate M and B, let's rewrite it. M is the expected value of yx minus the expected value of y times the expected value of x. Please note that these are not equal. Yeah, not equal. Divided by expected value of x squared minus expected value of x squared. And notice that these are not equal. Okay, so in order to calculate M, and we'll worry about B in a minute, I need to calculate this quantity, the expected value of y times x. I need to calculate the expected value of y and x. And I need to, x squared. And then, oh look, I can use the same quantity in both places here. So I need 1, 2, 3, 4 expected values. All right. So I've already got a column for 2 of those. So I just need 2 more columns. I need to know what y times x is, and I need to know what x squared is. All right, and then down here, I will calculate their expected values. So as I do this, I'm going to write this out of shot. I'll do this in a Python interpreter so I get the numbers right. So there is an Excel file on Canvas that, if it's not available, will be by the time you see this video. And it will let you do this automatically, so you don't have to do this step by step. I recommend understanding how to do this. But the Excel file basically will let you make your own homework problems. You can practice this, you can experiment with messing with the values, and you can, and I'll walk through that in future lectures. All right, so what I did was I summed up all of these points here and divided by 5 to find the expected value. So our approximation of the expected value. Basically, I found the average of this data set. I'm going to find the average of this data set. So I've just found the expected value for X. I'm going to look for the expected value of Y as well. All right, and so that's going to be 0.4 plus 2.1 plus 4.3 plus 3.3 plus 1, and all divided by 5. Whoops. Keystroke error. There we go. Yeah, that seems about right. So 2.22. Lovely. All right. So now, to get x times y, I need to actually multiply each of these to calculate x times y for every individual data point. So 0.1 times 0.4. Right? I don't know why I need the calculator for that. Actually, I really don't need the calculator for this. This is just going to be 21. This is going to be 86. Yeah, this isn't so bad. So 33 plus 16.5, I think. So let me actually do it so I don't make any mistakes. Pretty sure I was going to be right, but yeah, there we go. Yep. 49.5 is 33 plus 16.5. Let's see, and then this one's, well, I'm really going to have to struggle with this one. Yeah, there we go. Okay, so now I'm ready to find that expected value. So these problems are a little tedious to work out by hand. I'm happy to do it, though, because once you've worked through it by hand a couple of times, you've really got a deep intuition for how the computer is doing this. So some of you will be asking yourselves, wait a minute, programs like Excel and MATLAB, they can do curve fits automatically. Like you can just do that. You can put a line through data. Well, this is how those programs do that. This is what's in the background. And the reason to walk through this hopefully will become clear in a little bit. It's because every now and then you don't want to trust the algorithm to just do it. You want to tweak it. You want to make your own algorithm that does a better job, or at least sometimes I want to write my own algorithm that does a better job. So sometimes I don't, shock and amazement, sometimes I don't trust Excel to do my thinking for me. All right, so 0.1, no problem, we can do that. X squared, yeah, this one should be pretty easy. And this one's going to be 400. My rows are a little goofy, apologies. There we go. Yeah, so, wow, what is 15 squared? I should know that. 255? 225. 225, yeah. Yeah, I should have known that. Apologies. And this one's just 25. There we go. All right, and now we just need an expected value for x squared. So the 0.01 really doesn't contribute much, but, you know, might as well include it. And you'll notice I am not rounding. Like, I am carrying as many sig figs as I can. That is on purpose. The reason for that is these two values on their own can be very large, but the difference between them might be very small. That requires, if you want to get an accurate number, that requires that you carry a lot of sig figs. Right? The way to fix that, actually, there is a way to fix that numerically. We're not going to talk about it just yet, but there are ways to deal with that, to prevent that from being a problem. Okay, so we've got all the numbers we need. Now we're ready to calculate our slope. So m needs to be the expected value for xy, is right here, minus the expected value for y is 2.22 times the expected value for x, which is 10.02. Okay. And all right, now we need the expected value for x squared. That's here. Do not use this squared. No. Use this, right? So this is going to be 150.002 minus, now we need the expected value of x squared, right? So here we go. 10.02 squared. All right, so what is m? Calculator. All right, for my numerator here, I like to make little notes in the margin just so I can, in case I goof up with my calculator, I've got them. I've got those numbers. I've got that as my numerator. All right, and here is my denominator. So, .0636 divided by that is about now what are the units on m? So there's my number. What does it mean? What does that tell me? Now let's give it physical relevance. Well, so let's look at the units of this equation. Y has units of volts, x has units of psi. So then xy has units of volts times psi. And x squared has units of psi squared. So volts times psi, volts times psi. Psi squared, psi squared. So volts times psi divided by psi squared, m has units of volts per psi. Does that make sense? It absolutely does. That's the number of volts that you get in your output per change in psi, in your measurement, right? Another word for this is called your sensitivity. That is, how much does the output of the sensor change per change in the measured quantity? And it's in volts per psi for our make-believe pressure sensor. Okay, so we've got a slope. Now we just need an offset, b. And so the slope matches the change in output per change in input over this data set. Now, but the slope, or excuse me, the offset, its job is to, okay, we've got the slope right. Now we need to make sure that the line actually goes through the middle of the data. No problem, we can do that. For that, we just need to borrow. This guy. There's the middle of the y data, and there's the middle of the x data. This will make it go through the middle of the data. So b is going to be equal to expected value y is 2.22 minus m, we just calculated, no need to, silly, 2029, I'm being sloppy with I'm not bothering to write units, how sloppy, and then this is 10.02. So the offset is in fact very small if we look at this. I'll go ahead and reach for my calculator just to make sure I don't commit any mental errors. There's no one in the audience to correct me. It's actually a little alarming. I'm used to having a class full of people to yell at me if I make a mistake. All right, 0.186. Yeah, we'll stop there. 1869. That's good enough. All right, now what are the units on B? Well, Y is in volts, M is in volts per psi, X is in psi. So B is in volts. So the answer is this. There we go. So that's your calibration. And this is how you do that when you're doing it for real. So you can imagine writing code that automates all of this. Now, it's not hard, right? You can imagine writing code that does all this. And this is how Excel does it in the background. All right, so I'm gonna stop there. I'm gonna split this into a lot of small individual example problems. So that was the second talk on calibration. Thanks for watching.